So previously you have learned about the two iterative algorithms, the Hebbian and also the perceptron. The some sort of the limitation of the algorithm and how the perceptron overcome the Hebbian limitation. But one thing, if you still remember, so most of our predicted output will be based on the binary decision, means that it will be either 0 or 1. So in some situation, they might be good that we have some sort of the probability output in terms of the tagging based on the sample set, because of the probability we give some flexibilities whether that thing should be fire up or not instead of the hard limiter. Instead, previously we just said if lower than theta, and then it will not fire up, which is 0. If higher than theta, it will be fire up, which is 1. But in this case, for the additive linear element, it will give some sort of the probability, which is 0.5 will be fire up, or 0.6 will be fire up. You can set that thing later on. So let's go to the algorithm or the additive linear element. So what is the difference between the perceptron? So in general, for the additive linear element algorithm, so the first step will be the same, to randomize the initial weight. So the second part will be the algorithm. The second step will be to compute just the left side of value. So the value of the left side will be straightaway pick up, and then later on the additive linear means that the part here is the linear function. For the linear function means that the output y here will be equal to the summation of input. So for this particular case, the output will be equal to the summation of input. So it will be quite different for the Hebbian, because Hebbian y will be straightway equal to t instead of the input. Whereas for the perceptron, your y is the output after you perform the thresholding process. So means that we have previously for the perceptron, we calculate the summation, we perform the threshold value, and then we give the value of y. But for this particular case, for the additive linear element, it will be a bit different. We just straightway take all the sum input as the predicted output at one condition. So that will be the second step. So the third step will be to the adaptation of weight will be based on this particular equation, means that W new equal to the W old plus N will be the learning rate, X is the input, and then we have here T minus summation. So means that whatever we have calculate here, so we calculate the error here is based on the T minus the summation of input. So this thing will be the equation of the weak adaptation for the adaptive linear element. So the same thing with the bias updating process. For the bias adaptation will be based on the B new equal to the B old plus N, which is the learning rate, and then T minus summation of input. Okay, so we try to use the algorithm by using the same sample, which is previous sample is based on the OR. So we use let's go to the step one by one. So the first step is to random the initial weight. So this is our random initial weight. So the next step is we just fill up everything. So the same thing with our previous algorithm, we just fill up all the samples inside of the table. So in this case 1 1 1 0 0 1 0 0 settled in terms of the input, and then also the target will be 1 1 1 0, then settle. So the next part is that we need to calculate the value summation of input for every step. So in this case we have 1 1 here, which is this thing will be 1, sorry, this thing will be 1, this thing will be 1, and then the bias here will be 0. So for the first step of the summation, this part will be 0, this thing will be 1 plus 1, which is our summation of input will be equal to 2. So previously, if you still remember, for the perceptron, we take this value and then compare with respect to the threshold, and then we put y as a y here. But in this case, we just straightway deduct t minus summation. So in this case, t will be equal to 1, and then summation will be equal to 2. So means that 1 minus 2 will be equal to -1. So we are settled. The next part is the weak adaptation. So the weak adaptation stage for this particular case is we have the W new equal to W old plus n x t minus summation. So in this case, for this part, the W new will be equal to W old is equal to 1 plus 0.5. Okay, and then x will be equal to 1, and then t minus y will be equal to -1. So for this particular case, the value will be 1 minus 0.5, which is in this case equal to 0.5. Okay, so that's the first part. So let's move on to the second part of W2. So W2 will be for the first item, W2 will be, previous one will be 1 plus 0.5. So the value here the same, will be equal to 1, and then t minus 1, t minus sum will be equal to -1. So in this particular case, we have 1 minus 0.5, which is equal to 0.5. So the same thing here, which is 0.5. So we go to the third step, which is the bias adaptation. B old is equal to 0 plus 0.5, and then straight away t minus summation. T minus summation equal to -1. So in this case, it will be equal to -0.5. So we have here -0.5. So we are settled in terms of the first iteration. Okay. So now let's move on to the second iteration, which is a 1 0. So for the 1 0 here, so first we do the summation based on the given value of W1, W2 and bias here. So in this particular case, in general, this part will be multiplied with this part, and then multiply plus this part will be multiplied with this part plus -0.5. So in this case, 0.5. Okay, let me draw that thing, so to make the things easy for you to understand. So let's say this is x1, x2, this is bias. So W1, this is 0.5, 0.5, and then the bias value also -0.5. Okay, so how we calculate the summation? If I factor here 1 0, so means that 0.5, okay, this thing 0.5 plus 0 plus -0.5. So that is the way we perform. So the same thing here, this is 0.5, so this thing will be 0, you don't have any value, so this is -0.5. So means that the summation will be 0.5 minus 0.5. So in this case, the summation of value will be equal to 0. Okay, so 0.5 plus 0 minus 0.5. So you have the value of summation of 0. So the next part is the t minus summation. So t minus summation in this case 1 minus 0, which is equal to 1. So the next part, we perform the updating process. So for the updating process, let's say for the iteration 2. So for the iteration 2 updating process for the W1, so W1 will be equal to W old, which is equal to 0.5 plus learning rate will be 0.5, and then later on our input equal to 1, x1 equal to 1, and then later on our t minus summation will be equal to 1. So in this case 0.5 plus 0.5, which is equal to 1. So this is will be equal to 1. So once you selected that part, we move on to the W2. Since in this case for the W2, x2 will be equal to 0, x2 will be equal to 0 here. So in this case, we can straight away say that your new weight will be equal to the previous weight. So in this case, straight away 0.5. So the next part is the bias adaptation. So for the bias adaptation, So your B all equal to negative 0.5 plus learning rate will be 0.5, and then T minus summation will be equal to 1. So in this case, the bias adaptation value, new bias value will be equal to 0. So in this case, it will be equal to 0. So we are settled in terms of the second iteration. So let's move on to the third iteration. So for the third iteration, we have the value x1, x2, 0, 1. So first part is we need to calculate the summation. So in this case, the summation will be 0 plus 0.5. Okay, this is 0 times 0 equal to 0 plus 1 times 0.5 equal to 0.5, and then plus 0. So in this particular case, we have the value of summation of 0.5. Okay, this is how I get it, 0, 0.5 plus 0. Okay, now 1 minus target minus summation will be equal to 1 minus 0.5 will be equal to 0.5. So the next part is the weight adaptation. So since x1 here is equal to 0, you can take the previous value of weight. Okay, and then the second part, so this is for the iteration 3. So for the W2 new equal to the W old will be equal to 0.5 plus 0.5 learning rate, and then x1 equal to 1, and then your T minus summation will be equal to 0.5. So in this case is 0.5 plus 0.5 times 0.5 equal to 0.25, which is equal to 0.75. So we just put here the value here will be 0.75. So the next part for the bias adaptation. So for the case of the bias adaptation, in this case, B new equal to B old is 0 plus 0.5, and then T minus summation 0.5. So in this case will be 0.25. Okay, so now we move on to the final part, which is the fourth iteration. So for the fourth iteration, in this particular case, we have the value of 0, 0, and then first we need to calculate the summation value. So this thing 0 plus 0 plus 0.25, so the value here will be 0.25. So means that T minus summation will be equal to negative 0.25 because of what? Target is equal to 0 for this particular case. So the next part, we do the updating process, the weight adaptation. So since x1 is equal to 0, we just pick up the previous weight straight away. So the same thing, x2 is 0, we just pick up the previous weight straight away. And then the third thing is in terms of the weight adaptation. So B new equal to B old will be 0.25 times 0.5, which is the learning rate, and then the next thing is the T minus summation will be negative 0.25. So for this particular case, I just calculate the value here. If you can see, 0.25 times 0.5 times negative 0.25. So in this particular case, 0.125. We just straight away put here 0.125. Okay, so we are set up in terms of performing the iteration process for the additive linear element. So we are up until this particular stage, which is we give some predicted output. So the next part is that we can test this particular value, the optimal value after we perform the training process. so that we can plug in the value into the neuron, and then how we can utilize that thing to predict some sort of the output. So in general, I just draw back everything. Let me move this thing a bit upward so that, yeah, okay. So if I draw back the model here, so this thing will be x1, x2, and then this thing will be our bias with some summation, and then this is some linear function. So for this particular case, x1, w1 will be equal to 1, okay, and then w2 will be equal to 0.75, and then the next part, the bias will be equal to 0.125, in which we calculate the predicted output of y prime. So for this case, so let's just plug in everything in terms of the x1, in terms of the x2, in terms of our theta, and in terms of our y prime predicted. So this will be x1, x2, this is the target, this is our y prime, which is the predicted output, in which it will be the linear function. So plug in everything, 1 1 1 0 0 1 0 0, and then also the target, which is 1 1 1 0. Okay, so settle. So the next part we calculate in terms of the value of the y prime. So we put here 1 1. So 1 1 here will be equal to, I just put my calculator maybe somewhere in here so that you can see. So basically for this case, 1 plus 0.75 plus 0.125, which is our predicted output, will be 1.8. I just put 1.88. Okay, so the second part will be 1 0. So since this is 1, this is 0, so we have the output will be 1.13. So the next part is x1 0. This thing will be 1. So in this case, 0.75 times 0.125, which is 0.88. And then the next part will be 0 0. So you have here will be 0.13. Okay, so this is the predicted of the calculated output. So for this particular condition, in general, for the classifier, you can select some sort of the threshold that can be utilized to segregate this data. So in this particular case, if you look at the sample, so this thing will be cluster 1, this thing will be cluster 2 that we wish to separate, because based on the target, this thing will be belong to the two separate cluster. So between these two separate cluster, if you look at the value of y prime, how you able to do the separation between these things is that you have this type of separation of the value. So in this particular case, if your value of selected threshold will be higher than 0.3 and then lower than 0.88, so for this particular case, you're able to separate this data well. So you can select some sort of the theta value. I'm moving this thing a bit upward. So if we select any theta value higher than 0.13, and then in this case lower than 0.88. So let's say I just put this thing maybe higher than 0.13 and lower or equal to 0.88. So for this particular case, if you select any value within this particular range, so in this case you're able to do the separation between these two data set. So however, the best thing for this particular case is perhaps you select the value that is optimal, which is the half of this particular case. So in this case, how I select the half of this particular case is actually the 0.88 minus 0.13, and then we divide by 2, half of that thing, and then plus the previous one. So we can say the 0.5, if you select the theta equal to 0.505. Okay, so for this particular case, the selection of the threshold will be able to separate this data in the maximum separation between these two data sets. So if, let's say, if we plot the scatter plot and then use this 0 theta will be 0.5. So we look at how the data or the decision boundary will be constructed. So let's say for this case, we put x1 here, x2, and then the same thing, if we put here value will be 1 1, and then this thing will be belongs to the cluster of 1, and then this thing will be belong to the cluster of 0. So the general equation for this particular case is the same thing, x1 w1 plus x2 w2 plus b, and then higher or equal to theta. Okay, so if we wish to transform that thing to the decision boundary, then this part must be equal to theta. So if we plug in back all the value, so in this case x1 will be 1, so means that the w1 will be 1, so x1 plus 0.75 x2 plus your bias will be 0.125 is equal to our selection of the theta 0.505. So for this particular case, your value of the x1 will be equal to negative 0.75 x2 plus I just deduct 0.505 minus 0.125. In this case, we have 0.38. So if I plot this particular equation, if x2 equal to 0, means that x1 will be 0.38. 0.38 maybe somewhere in here. And then the same thing, if x1 equal to 0, then x2 will be 0.38 over 0.75. So in this case 0.38 over 0.75, so it will be 0.51. So 0.51 may be somewhere in here. So in this case, we can draw the optimal decision boundary for this particular condition, which is this part. So this is in a situation where we select the value of theta which is equal to 0.505. So let's say in one situation you pick up some sort of the theta value maybe near to 0.13. So let's say I just select our theta will be 0.15, which is near to this side. So what will be happening to our decision boundary? So for this case, let's plug into the same equation, only I just put a different value of theta. So in this particular case, x1 equal to 0.75 x2 plus 0.125. Oh, okay, sorry. I just use so in this case x1, okay, plus 0.75 x2 plus 0.125 will be equal to 0.15, which is our select this type of the threshold value in our based on the ranging of the theta. So in this case, x1 will be equal to the same thing, negative 75 x2. So in this case, plus we have 0.15 minus 125, which is 0.025, 0.025. Okay, so this is our decision boundary if we select the value of theta equal to 0.15. So if x2 equal to 0, then x1 will be 0.025. 0.025 means that the value will be very near to this side. Okay, and then the next part, if x1 equal to 0, then x2 will be equal to 0.025 over 0.75. So in this case will be 0.03, which is very near to this part. So if we draw that thing, so let's say in this case I just use pen because of it's quite near. So if I draw it, will be somewhere in here. So this is the meaning. So if you select the value very near to here, so means that your decision boundary very near to this side. If you select 0.88, so means that your decision boundary will be near to this particular side. So the optimal one will be, of course, we want to ensure that the decision boundary will be in the middle of this part. So what we do is that we just deduct 0.88 minus 0.12 and then divided by 2, which is over 2, and then plus the first initial part, in which we will obtain the optimal value of the 0.505 for the additive linear element. So that's it in terms of the additive linear element. Thank you.